So I want to go over some more examples of substitution because it's a very important technique. It's a very powerful integration technique. A lot of integrals are done this way, so it's very important to have this one down. So let's look at some other cases. So there's kind of like a lot of different ways that this one can pop up, and like they all will have like little subtle differences. So we want to really understand like exactly what is going on with the substitutions. Okay, so like on this one, for example, if we go ahead and make the substitution, okay, so first of all, why would we want to make a substitution here? Well, there's really no good algebra way to do this one necessarily. You could maybe try to multiply by the conjugate. That might work. It'll probably get a little messy. Just thinking off the top of my head, I think that it would probably work, but it would definitely be a little messier than the substitution method would. But essentially what's happening here is that, there's really no good way to deal with this square root part, right? So what we can do here is we can do a substitution for the stuff inside the square root. Okay, so then du in this case is just equal to dx, right? Because the derivative is just 1. So you might think it really doesn't accomplish too much. But notice that, this implies that x is equal to u plus 1, which is what the top is. Okay, so we're making two different substitutions here. So this is a fine thing to do. We let u be one thing, and then we can, if there's another one of those variables, we can go ahead and rewrite that one as well. So this means we're going to end up with u plus 1 over the square root of u du. So why is this one easier? Well, now we can split up that fraction. So this is u over root u plus 1 over, and I'm just going to write it as two separate integrals at the same time, actually, plus 1 over root u du. Now it's just two straightforward power rules. Okay, so a lot easier to work with. So this is u to the 1 minus 1/2, right? I'm just using the exponents. This is to the 1 power, this is the 1/2 power. So we subtract them. So u divided by root u is actually just root u. And then this is u to the negative 1/2 du. So u to the 1/2 is going to be u to the 3/2 over 3/2. U to the negative 1/2 is u to the 1/2 over 1/2. And then we have a constant. You don't need two constants, so you can just combine them into one constant. So then that's equal to 2/3 u to the 3/2 plus 2 u to the 1/2 plus c. And then we just want to make our substitution back. So we let u be equal to x minus 1. So we just go ahead and say this is 2/3 x minus 1 to the 3/2 plus 2 times x minus 1 to the 1/2 plus c. And that would be our final answer. Okay, for the next example, let's actually look at one where we're doing a definite integral. Okay, here we're just looking at taking the indefinite integral. But how could we incorporate this into ones where we're taking the definite integral? Okay, so let's do the integral from 0 to 1 of x times the square root of 1 minus x squared dx. Okay, so there's two ways we can approach definite integrals of substitution. We could either just evaluate the, we could just find the antiderivative using substitution and then use that in the definite integral like we would. We could sub back in x, and then we could take that and use plug in the bounds. Or when we make the substitution, we can also change the bounds with that substitution. So for example, if we let u be equal to 1 minus x squared, then du is equal to negative 2x dx. But then we can also go ahead and plug in the bounds and see what the bounds would be in terms of u. Okay, so since u is equal to 1 minus x squared, if x is equal to 1, then u is equal to 1 minus 1, which is 0. And if x is equal to 0, then u is equal to 1 minus 0, which is 1. Okay, so we can change the bounds as well. Again, you don't have to. You can just find the antiderivative using this method, plug x back in, and then go back and plug in the bounds. But this is kind of a cleaner way to do it all at once. Okay, so our bounds change from 1 to 0. And then we have also notice that this part right here is not exactly what we have on the outside, right? The negative 2x dx. So we'll want to bring that negative 2 over. Okay, so I'll just do it right there so I don't have to rewrite it. So we'll bring the negative 1/2 onto the outside since that's a constant. And then we have the square root of u du. Okay. And then we can go ahead and integrate that. And we're not even going to need to sub the x back in because we changed the bounds and this is a definite integral. Okay, so this is negative 1/2. This is going to be u to the 3/2 over 3/2. And then we're plugging in u equals 1 and u equals 0. Okay. So negative 1/2, 0 over 3/2. I mean, you could just write 0 minus 1 to the 3/2, which is just 1 over 3/2. Okay. So this is ultimately going to be negative 1/2 times negative 2/3. Okay, so we're just going to get 1/3. So a bit of a different situation here, where you don't end up having to make that last substitution because we just went ahead and substituted the bounds instead. Okay. Okay, let's look at another example here. Okay, let's look at a trig example. Okay, so like we saw what the antiderivative of sine and cosine were, but what about the antiderivative of tangent? Okay, that one we kind of skipped, and the reason is that we kind of needed this method in order to evaluate it. So if you remember, tangent is equal to sine over cosine, okay, dx. And sine and cosine are derivatives of each other, right? One of them having a negative. So now we can go ahead and we can make a substitution here. I'm going to make the substitution with the bottom one, and you'll see why after we go ahead and do this. So if we let u equal to cosine of x, du then will be negative sine x dx. Okay, so we can just bring that negative over to the other side. So this is going to be negative du over u is how we could write it here. Or you could just write 1 over u du. So we often like to write it like this because this is kind of like the derivative of u divided by u, which is what the form of the natural log is. Okay. I mean, you could just write it as 1 over u du, and then same thing, right? The antiderivative of 1 over u is the natural log. So regardless of how you think about it, this is going to be negative natural log. Remember, it's the natural log of the absolute value of whatever it is, because we can't guarantee that that argument is negative without that. Cosine in particular is, negative often. So we definitely need the absolute value here. So negative natural log of cosine of x plus c. So, as I've said, we're not really going to do trig, but I just use this one in particular because this is a good form to remember, particularly when you have like the derivative of something divided by itself. This form is going to pop up a lot. So, just as a simpler example of what I mean, like if we had like if we just had x squared over like 2x, for example, even something as simple as this, you're going to end up getting the natural log. And it's easy to see here because you just cancel an x and then you have 2 over x, and then of course you're getting the natural log, right? But just in general with this form, with more complicated functions, you end up getting the natural log. So like if we were doing maybe something like 1 over x natural log of x dx. Okay. For this one, we can let u be equal to the natural log of x, and then du is equal to 1 over x dx. Okay. So then we're going to have the integral of 1 over u du again. So we're going to get natural log of the absolute value of u. So that's going to be equal to the natural log of the natural log of x. Okay, still need the absolute value here. Sometimes you can drop it if you know the thing on the inside is positive. Natural log of x needs positive numbers on the inside, but it can't output negative numbers. So we definitely need the absolute value symbol here. So anyway, I just wanted to say, substitution, like I've said, it's very important. It comes up in, I just feel like you use it like pretty much every time you do an integral. Like, maybe that's just in my head, but I just feel like anytime I have to like integrate something, whether it's in probability or statistics or whatever, whenever I was doing them, like you always would be doing substitution. So definitely one of the most important parts to practice. Just doing a lot of problems and kind of getting the rhythm down and kind of starting to recognize what thing you want to let u be equal to. That'll come a little bit easier with practice.